Okay, let's talk a little bit about rainbows. Rainbows are kind of a fun topic of conversation because we've all seen a rainbow out there. Probably some of you have seen a double rainbow. It's glorious. One of my kids' favorite videos is the double rainbow. So, how do rainbows work? Rainbows work because of something called dispersion. So remember when we were talking about the index of refraction with geometric optics, right? The index of refraction, n, came into the speed of the wave. V is c over n. But n is not just some fixed number. It actually depends on the wavelength. The index of refraction depends on the wavelength that you're talking about. So, when I go from air into glass, and let's say I'm using sunlight. So, we know what happens, right? The sunlight, when it goes into the glass, it's going to refract. It's going to bend at a different angle. So if this is the normal, it's going to bend. So it's going to bend this direction up if it's red. If it's green, it would come down here, and then blue would come down here. Red, green, and blue. And this is because the index of refraction of glass depends on the wavelength. And through red, for this particular glass that we're talking about, it's 1.520. And for green, it's 1.526. And for blue is 1.531. And so blue is a shorter wavelength, so it has a higher index than the red. Now, I didn't draw this to scale, so these things aren't going to be nearly spread out this much. But these numbers are pretty close to being equal. We just did this for simplicity here, okay? So you're all familiar with this because you've all seen a dollar bill, and you've probably seen it looks like the Illuminati, the dollar bill pyramid, and they're sending in white light into this prism. So it looks like this. And what happens is the different colors spread out, and coming out the other side of the prism, you get three different beams. Okay? And so the top one is so this is white light. And so the bottom one's going to be blue. The top one would be red. And so the top one sees a different index. Then there's a law, Snell's law, which tells us that the incident times the sine of the incident angle is the index of the transmitted wave times the angle or the sine of the transmitted wave. Okay? So if you flipped a dollar bill over, on the back, you would see this picture. If you look through the dollar bill, you would see these reversed. Okay, so one of the ways would be correct, and if you flipped it over, it would be incorrect. All right? And the reason it's incorrect is that most glasses behave exactly the same. I'm just cleaning this side of the glass. Just this side, the right. Your left. So for most different types of glass in the optical region, we've got the N over here, and the N will decrease with a wavelength. Okay, so this is the wavelength. So long wavelength is red, short wavelength is blue. So blue has a higher index than red. So blue bends more when it goes into glass than red. And this whole thing is just called dispersion. So how do we understand rainbows with this picture? And you probably have noticed this, but you have to be in front of the sun at your back to see a rainbow. The sun has to be behind your back. All right? So rainbows arise from dispersion. All right? So we're going to draw a picture of this thing. So here's the sun. Okay? Here's a cloud. And it is going to be raining. So here's these droplets of water coming down. Okay? Sunlight is going to bounce off these things and come back to you, and you're going to observe the rainbow. So first question. Here's the Earth. Where are you in this picture? If you're standing on the Earth somewhere, are you directly under the cloud? Are you over here next to the cloud, or over here next to the cloud? Where are you standing when you observe a rainbow? Anybody know? You are right here. Okay, if you're over here, you don't see a rainbow. If you're right under the cloud, you don't see a rainbow. Anytime you see a rainbow, the sun is going to be behind you, always. So try that. Next time you see a rainbow, turn around, look right behind you, and that's where the sun is. All right? And this is why you can never get to the rainbow, because as you get closer, the rainbow moves further away. It's very annoying. So what happens? Here comes the sunlight. It's going into these water droplets, right? This is, of course, water. Something happens, and all these different colors start to spread out. And so you see the rainbow when you look up. So let's see if we can figure out what is actually happening in these water droplets. So we're going to do what physicists always do, assume a spherical water droplet. And now, so we've got sunlight coming in. Sunlight, of course, has all the colors. One of those colors is red. Okay, so let's map out where red goes. When red comes into the water droplet, it bends a little bit. So this is red. It hits the back, and it comes down, and now it bends again on the way out. This is our red ray of sunshine. But blue is also in the water droplet, and when the blue comes in, it's going to bend a little bit more. Okay? So it's going to bend down further in the water droplet. It hits the back of the water droplet at a lower point than the red, and so it's going to bounce back a little bit more horizontal. And so when it comes out, it's going to come out, actually be more horizontal than red. So it comes out here, and this is how the color separation works in a water droplet. The different index of refractions, which depends on the wavelength, tells you that the red is going to bend a little bit less than the blue. And with the bounce off the back of the raindrop, bounce off back, the blue comes out at a little bit higher angle than the red. So when you look up in the sky and you see a rainbow, what that means is that you have to look at a higher angle to see the red, okay? A lower angle to see the blue. So when you look at a rainbow, red is on the top and blue is on the bottom. And you can convince yourself that pretty quickly based on this geometry. But if you see a double rainbow, which is really cool. Anybody seen a double rainbow? You see them also when you're on an airplane. So a single rainbow would be red, and then green, and then blue. So a double, oh, I forgot green. So a double rainbow, there is a dark band, and the dark band in between them is actually called Alexander's dark band. And then if you keep looking up in the sky, and the conditions are just right, you'll see a second rainbow up here, and it'll be reversed. So the second rainbow will be inverted. It'll be red to green to blue, okay? Dark in between, and then it's inverted. And so, if the first rainbow comes about from this phenomenon, what do you think creates the second rainbow? What happens in the water droplet to create a second rainbow up higher up? Anybody know? It turns out that it bounces twice in the water droplet. Okay? And so, in fact, it goes the other way. It goes around this way and bounces twice, and that creates this inversion of the first rainbow. And it also means the second rainbow is a lot dimmer than the first rainbow. This one's pretty bright because a lot of that light comes off from the first bounce. But there's two bounces in the water droplet, so a lot of the light is lost. And so it's usually really hard to see a second rainbow just for that reason. It's much dimmer than the first rainbow. Right? So that's the dispersion of light.